So effectively today will be the 17th lecture of high-speed communication circuits. You can see also this as RFIC, radio frequency integrated circuits. That is another name for this subject. What we will do is we will discuss about mixtures today. As you know, we already discussed the communication circuit, heterodyne circuit, heterodyning or mixing. That we discussed earlier. In mixing or heterodyning, what is done is we multiply the received RF signal with a local oscillator signal. So when you multiply them, two frequencies like sin omega 1t into sin omega 2t, resultant is sin omega 1 minus omega 2t and sin omega 1 plus sin omega 2, sin omega 1 plus omega 2t. Then you use a filter. If you use a filter to filter out the higher frequency omega 1 plus omega 2, then we will get only omega 1 minus omega 2. So that is called the intermediate frequency. That is what we have seen in the beginning of our discussion on this topic of this course. So the important part is the mixture part, or the part where we multiply two signals of different frequencies. RF is a signal of some frequency and local oscillator gives you another signal with another frequency, and we are multiplying them. Usually in the circuit, when you design the circuit, what you will do is antenna. After the antenna you have a filter, RF filter. Then after the RF filter you have the low noise amplifier. After the low noise amplifier you have the mixture. Now between the antenna and low noise amplifier there must be proper matching, so that the signal that is received by the antenna is properly transmitted to low noise amplifier without loss. With minimum loss it is transferred to low noise amplifier. Then low noise amplifier is to be matched to the mixture. This is what is to be done in the circuit design. To do this, usually when you design a circuit, when you design the IC package, in the package at a time design the LNA and the mixture. So if at a time if you are doing the LNA and the mixture, then the input impedance of the LNA is the input impedance of the total circuit. LNA and mixture circuit will be the input impedance of the LNA matched that to the antenna, and that is for maximum power transfer. Now in doing this, designing the mixture for integrating it to LNA, there are some design issues. First is the noise figure, because noise figure impacts the receiver sensitivity. Then the linearity, because linearity will impact the receiver blocking performance, how much the receiver will block. Then the conversion gain. Conversion gain is it lowers the noise impact of the following stage. Next stage, the noise impact will be lowered because of the conversion gain. This is usually called the voltage conversion gain also. Then power match, because you want maximum voltage gain, therefore you want power to be properly matched between stages. So we want maximum voltage gain rather than power match for integrated design. As I told now, LNA and mixture, they have to be integrated in the design. Then power, we want less power dissipation, so their battery life will be high. Then isolation, you want to minimize interaction between the RF, IF and LO ports. So say they should not interact with each other, that the power should flow seamlessly from RF to IF stage, from IF stage to between the RF and LO stage, that should be seamless flow. So RF, LO, they should come seamlessly to the mixture, giving rise to IF. Then sensitivity to process and temperature variation. This is always important in all designs, because this makes it this needs to make it manufacturable in high volume. Whatever you are designing, you design in high volume. Now let us look at ideal behavior of the mixture. In the ideal behavior of the mixture, you see what we do is RF input is there. Look at the top left figure. In the top left figure, we see the RF spectrum. The RF spectrum is the RF is at the desired channel will come at a frequency which is slightly deviated from F0. So the small deviation is delta F. So that is where your desired channel is. RF frequency is centered at 0. So RF input is F, take that as 0. So from that, on both the sides, plus F0 minus F0. So plus F0 plus delta is the desired channel. Similarly, minus F0 minus delta is the desired channel. That will be given as input, one of the input to the mixture. The other mixture input to the mixture is the local oscillator. From the local oscillator, we will get the frequency exactly at F0. Since we will get the frequency exactly at F0, you can see the spectral diagram, which is the left bottom left diagram. In that, you can see at plus minus F0 at the local oscillator, there is the impulse, which is actually for cos. That is in the frequency domain. Therefore, you see this one, the arrow sign with 1, that shows you the cos. And because 2 cos omega t means at F0 1 cos omega t, at minus F0 1 cos omega t, total is 2 cos omega t. That is the LO output. Now when you take them, multiply these two, RF and the local oscillator output, then what will happen? When you multiply this the signal at F0 with signal at delta F0, then delta F0 signal will be shifted to the right side and to the left side by an amount of F0. So from F0 it will go towards right side by an amount of F0. From F0 it will come towards the right side by an amount of F0. That is what is shown in the bottom right figure. So in the bottom right figure, you can see the IF output is around spreading over delta F plus minus delta F on both sides of 0. Then F0 plus minus F0 is on both the sides of 0. So from plus minus F0 it has shifted towards left. Then there is the undesired component, which is F0 plus delta F. Now using the channel filter, using the low pass channel filter, we can remove the undesired component and low pass frequency will pass, therefore this delta F will pass to the channel. So if IF, as I told you, IF is for intermediate frequency. If intermediate frequency is non-zero, then we call it heterodyne or low IF receiver. If intermediate frequency is 0, IF frequency is exactly equal to 0. IF means F0 minus delta F, that is equal to 0, then we call it to be homodyne receiver. So F0 minus delta F is equal to 0, or F0 is equal to delta F, or when delta F is exactly over F0, in that case it is homodyne receiver. Now the issue of image aliasing. Aliasing means overlapping, so something like overlapping. Not exactly overlapping, but it is something like overlapping. Now look at this figure, the first figure. The figure on the top left, that is the first figure. So what we have here is, we have the RF, and then we have the desired channel. In the RF we see the desired channel is at delta F, and so from F0 if I move by an amount delta F, the desired channel is there. If I move to the right of the F0, if we move to the left of the F0 by an amount delta F, then there is the image interferer. So this is possible, and assume that this is existing. The image interferer is also there in the RF. Assume that. If the IF frequency is non-zero, this image band for a given desired channel band, this will always contain an image band, and it will combine with that of the desired channel at the IF band. That you can see in the bottom figure, bottom right hand figure. Left hand figure, you know, left hand figure is the spectrum of the LO output, local oscillator output. LO means local oscillator. So spectrum of the local oscillator output is on the bottom left. So if you multiply these two, the top left and bottom left, if I multiply them, then what I will get is the right hand side, bottom right hand side. So in the bottom right hand side, what has happened, and that you need to understand, minus delta F is translated toward to the left of the 0, and plus delta F similarly is translated towards the right of the 0. So those two red signals are on the left and right. Then you have the desired channel. So desired channel near the 0, the desired channel overlaps the image interferer over the frequency band of delta F. And what happens to the other part, delta F plus F0, that will move towards the right hand side of the F0, or to the left hand side of the minus F. That we can easily filter out, or the part which has moved beyond plus minus F0, that can be filtered out using the image rejection filter. So only part is this part where they have overlapped. Image interferer and the desired channel, they have overlapped. Now since they have overlapped, if you use a filter, you cannot remove them, remove the image interferer from the desired channel. Why? Because they are over the same frequency. Since they are over the same frequency, if you remove that, filter is filtering out frequency. So if you remove out the image interferer over the frequency, over that frequency also is the desired channel, so desired channel also will be removed. So we cannot use a filter to remove the image interferer. So there will be image aliasing. Then another problem is local oscillator feed through. LO feed through is another problem. in now you can see this figure is the same as the earlier figure of uh, image interferer, except that if you look at the circuit in this figure, which is the top right hand side, then you can see the local oscillator output that also is fed to the IF output. So that is multiplied with RF. Also some of that will leak out. So that will be fed to the IF output, that is called the feed through, which leaks out, that is called the feed through of local oscillator. So LO feed through, this will occur from LO port, local oscillator port, to the IF output port. Why this will occur? Because of the parasitic capacitances, power supply coupling, etc. present in the circuit. So through those parasitic capacitances, they will be fed through to the output. This is usually significant if the LO output is much higher than the RF signal. Otherwise, it will be suppressed. But if it is very high compared to the RF signal, then it will be significant. Mostly this is not significant. Mostly LO output will be small compared to the RF input to the mixture. But if it is very high, then it will be significant. If it is very large, this can potentially affect the sensitivity. So potentially desensitize the receiver due to the extra dynamic range consumed at the IF output. If small, it can be generally removed by filter at the IF input. Then there is another thing which is called the reverse LO feed through. So LO feed through towards the IF output is called the LO feed through. LO feed through towards the RF input is called the reverse LO feed. So this is the only difference. The reverse LO feed through, this will occur from LO port to RF input port, again due to parasitic capacitances. Mostly these feed through are because of parasitic capacitances. If it is large and LA does, low noise amplifier that does not provide adequate isolation between the antenna and the mixture, then LO energy can leak out to the antenna and violate emission standards of the radio. So we must ensure that this is isolated from the antenna properly. Adequate isolation from the antenna is necessary. Then comes this part, the self-mixing of reverse LO feed through. So what is self-mixing of reverse LO feed through? This is basically in the RF. When the RF is coming, as I told you already in our discussion, that F0 is greater than the RF. So F0 is greater than the RF, local oscillator output, local oscillator frequency should be at least equal to RF or greater than RF. So if that contains a component of F0, the RF contains a component of F0, then what we get is called reverse LO feed through at F0. Then you have the desired channel, then you have the image interferer. These two will always be there. Desired channel will always be there. That is what we are going to process. Image interferer, we will see how to remove that later, but we cannot use a filter that we have seen. So desired channel, image interferer will be there. In addition to that, at F0 in the RF spectrum, there will be a component at F0 because that comes from the reverse LO feed through. So self-mixing of reverse LO feed through is important because of this presence of this FO or F0, or the DC and F2 F0 components will be created at the IF output. This is of no consequence for a heterodyne system, but can cause problems for homodyne system because IF is 0. Now, once we know what are the signals or which can cause problem like image like feed through, forward feed through, backward feed through, and or reverse feed through, etc. Now let us come to on the next part, which is removing the image interference. So the first solution to remove the image interference is this. What we do is, first you consider the LO feed through. So LO feed through will be at F0. Since LO feed through is at F0, when you are doing the mixing, so that F0 will be translated by an amount of F0 to right and by an amount of F0 to the left. So when it comes to the left, it will be at the origin 0 and or at the DC, and when it goes to the right, it will be at 2 F0. So from F0 it will be going in this manner. So the other signal, the desired signal will be beyond 2 F0, that will be the F0 plus delta F, and F0 minus delta F will be near the DC. So the near the DC will be delta F. So an image rejection filter that can be used before the mixture. In this case, what we do is use an image rejection filter before the mixture. So if we use an image rejection filter before the mixture, this will prevent the image content from aliasing into the desired channel at the IF output, because you have used an image rejection filter. So that filter will be a bandpass filter, so hard type of thing. So if it is a bandpass filter, what we will do is you will remove the band in which the image is there. So that band will be removed, only the desired channel will pass through that. So before, whatever is before the image into the desired channel, those parts will be removed. So remove that using an image rejection filter. This is one solution, using an image rejection filter. But the problem is the bandwidth of the filter must be large enough to pass other channels. All channels must pass. So that should be the bandwidth of the filter, and filter Q cannot be arbitrarily large. If it is arbitrarily large Q means bandwidth is small. So to have large bandwidth, filter Q should be small. Now consider the second solution. In the second solution, what you do is we directly mix down to the baseband. So what is done here is it is like a homodyne approach. So with the IF frequency of 0, there is no image band, so image band is automatically removed. Now what are the issues? The first issue is it becomes, instead of heterodyne, it becomes homodyne. That is the first issue. There will be a DC term of LO feed through, which can corrupt the signal. It is time varying signal. DC offset can swamp the dynamic range of the IF output. Then 1/F noise and back radiation through antenna, all these are possibilities. Then the third solution. Third solution is using a mixture. So this mixture is called the image reject mixture. So with the original mixture, you use another mixture, use or design an image reject mixture instead of a simple mixture. In the image reject mixture, what we do is we use balance modulator. So there are two balance modulators, you can see. And both these balance modulators are fed from local oscillator in phase quadrature. So if to the top balance modulator we are giving cos omega t, to the bottom balance modulator we are giving sin omega t. They are in phase quadrature. 90-degree phase shifter is there. So local oscillator directly it goes to the top balance modulator. From local oscillator it goes to a phase shifter, 90-degree phase shifter, then goes to the bottom balance modulator. Then after the bottom balance modulator, again it goes to a minus 90-degree phase shift, and then they are mixed. The top balance modulator and bottom balance modulator outputs are mixed. Then they pass through a low pass filter or band pass filter, and then it goes to the IF. So in this way, image is rejected by similar method to this is the method of generating SSB or single sideband modulation. So single sideband generation like this. Image rejection is limited by amplitude here, and phase matching of RF and a low pass 40 dB image superposition is typical here. RF filter can reduce the image further if necessary. Otherwise, the RF image reject filter can be omitted. Now let us have a frequency domain view of the image reject mixture. So first is we have the RF, then we have the FLO, local oscillator frequency. Then with the local oscillator frequency we have FLO minus IF, that is the desired signal, FLO plus IF, that is where the image occurs. So that is the top frequency, top top figure. Then come to the next figure. In the next figure, RF is multiplied with cos 2 pi f0t, so it means the frequencies are at plus minus f0, which is the middle one. So you can see that if you multiply that on these two, then what will happen? The red will be superimposed on the blue part. On both sides of the DC, red will be superimposed on the blue part. So this here what we do is we ignore the components around plus minus 2 FLO because they can be filtered by IF filter. So only this part we will consider around FIF. So plus minus FIF we will consider the frequency. Then come to the third one, where you have the phase shifted version sin omega t. Or top, middle one is for cos omega t, bottom one is for sin omega t. In the sin omega t at f0 plus minus f0, you will have minus j and plus j amplitude of the signal. So that will be there. This green is, you can see the amplitude is minus j and plus j at f0 and minus f0. So multiply them. If you multiply them with the RF signal, original RF signal, then what you will get is the figure shown on the right hand side, because one is bottom or downward is minus j. So this one will, the image will be towards the bottom one. Similarly, the f0 j plus j is upward, therefore image will be in the upward direction. So here again you ignore the components around plus minus 2 FL. Now what we have got is, from cosine we have got the top one, which is the superimposition of image with the desired signal. Then the bottom one, from the sine we have got the superimposition in the opposite direction of the image with the desired signal. So image is topward, top in the top direction, then desired signal is in the bottom direction, or image is in the bottom direction, desired signal is in the top direction. Now if that Z is going to again minus 90 degree, then what will happen? Because of 90 degree phase shift, this will flip the portion which is on the J, that will again flip. So on the image signal will come to the downward and the desired signal will go in the upward direction. Now if you add these two, Y and Z cap, if we add these two, then what we will get is image in the Y is in the upward direction, image in the Z cap is in the downward direction. So they will cancel each other, and desired signal in both case Y and Z, they are in the upward direction, so they will add up. So you will get a strong desired signal, image signal will be completely removed. So this is the principle. So we can see that image is completely rejected regardless of RF input fetch. So this is again the same circuit, YT, ZT, then Z cap T, then IF out. The advantage is it allows low IF frequency to be used without requiring high Q filter. It is very amenable to integration. It is easy to integrate using this. Designing integrated circuit is easy with this. Disadvantage is level of image rejection is determined by the mismatch in gain and phase difference path, and practical architectures are limited to about 40 dB image rejection. Then we will consider an alternate implementation. Instead of going through two phase shifts of 90 degree, how we can achieve this. So again here you can see we have the image interferer and desired channel, and that is for the RF. That input we give to two local oscillators. One local oscillator is 2 cosine 2 pi f1t, other local oscillator is 2 sine 2 pi f1t. So output of those mixtures will be, so those two mixtures, then those two mixtures output are A and B. Then A and B, they go through the low pass filters to give you C and D. So from A goes through low pass filter, gives C, B goes through low pass filter, gives D. Then C is again mixed with cos 2 pi f2t to give E, and D is mixed with 2 sine 2 pi f2t to give G. Then E and G are subtracted to give the IF output. We will see its frequency domain analysis, from which we will see that we have rejected the image. So here what is the advantage? We have avoided 90 degree phase shifters of the signal. Besides 90 degree phase shift of LO outputs, it is much easier to realize using quadrature VCOs or frequency dividers. Mostly we use frequency dividers to generate cos and sine. Now let us look at the principle step by step. The top figure we have already discussed what is it. Then let us come to the bottom figure. In the bottom figure, if you look at the top one of the bottom figure, which is the middle figure, there are three figures: first row, second row, third row. The second row, that gives you what happens to the signal as it travels from A to C to E. So from A to C to E, what is happening, that is given there. So what has happened here? At A, after A, what has happened? At A, we are multiplying with cos. So if you are multiplying with cos, so at plus minus f1, there will be a signal present. So that signal is present. So spectrum, you can see the blue one is at plus minus f1. So that when we multiply that with this the RF signal, what you will get is shown on the right hand side of the middle row. And we do not want anything at plus minus 2f1. So that will be thrown out. So using a low pass filter, just use a low pass filter around the DC, which is below F1, which allows patching the frequencies below F1, so everything above F1 is thrown out. Similarly, look at the bottom figure, bottom row. In the bottom row, because of sign, we will get at plus F1, we will get minus J, and at minus F1, we will get plus J. So that if you go to the figure, if you multiply that with the RF input, so multiplication is basically convolution using the convolution in frequency domain. This gives you the figure that we saw on the bottom right hand side. So the image on the negative side is on the top, image on the positive side is on the bottom. Then you have the desired signal on the negative side is in the bottom, desired signal in the positive side is on the top. Others are filtered out using the low pass filter.
Hi, you have reached Professor Mishra. Please wait while I connect you. Hi, you have reached Professor Mishra.
And now come to the second step. In the second step, what we do is, after the filtering, what we have got is, the second step shows what we get after the filtering. So the middle row, that shows what we get after the filtering at C. So what is the C? Frequency is the frequency domain of C and frequency domain of D. These two are shown here. Because other part we have filtered out, use the low pass filter. So as shown in the previous figure. So after the low pass filter, this is what you will get in the frequency domain. So then you come to the third step. In the third step, look at the top one, the first one, C. C goes into again cos 2 pi f2t. So if that goes to cos 2 pi f2t, you will get what is shown in the top. So C goes to cos 2 pi to 2 pi f2t. So that will give us the spectrum that is shown at the middle one. So f22 is to be so chosen that the image that the spectrum will be distributed around the C. So in the spectrum we will have both the image and the desired signal in the up direction. Then look at the G, which is you give the D to the G sin omega t. So that will again give us the spectrum which is shown in the bottom. So bottom spectrum, you can see here the image is in the upward direction and the desired signal is in the bottom direction. Now what we will do is we will subtract the G from E. So if you subtract G from E, then image will be subtracted, whereas the desired signal will be added. So image will be subtracted, image signal will be, desired signal will be added, so image is removed. So ultimately image is removed. Using that, ultimately image is removed. Use a band pass filter or low pass filter around this signal, the desired signal, and you can recover back the IF output. Now in this, what are the issues? Issue is, if you are using analog architecture, then you require additional mixtures. We are using additional mixtures. Additional mixtures, they will introduce more mismatch and noise. because of these more mismatch and noise. This is limiting the image rejection and noise figure. Those will be limited. So this can be fixed by digitizing C and D, then by performing a final mixing at the digital domain. So from analog you just shift to digital domain. This can generate accurate quadrature sine wave signals by using frequency divider. Instead of using VCO, use frequency divider. Now, suppose RF in the F is purely imaginary. If RF in the F is purely imaginary, which means sine wave. So if it is sine wave or purely imaginary, in the frequency domain you can see the spectrum on the left hand side, and the right hand side is the circuit. So in this case, both desired and image signal both will disappear. So if this happens, both will disappear using this circuit. So architecture is sensitive to phase of the RF input. Now the question is, can we modify this architecture to fix this issue of disappearing? So what we do is, the desired channel in the mixture, what we just interchange cosine and sine at E and A. So at E, earlier we were giving cos, now you give at E sine. Similarly at G, we are mixing it with sine, now mix it with cosine. Only this must change. So desired channel, now it will appear in given two changes, these two changes. Sine and cosine demodulators are switched in the second half of the image rejection mixture. The two paths are now added rather than subtracted. So the issue is, the architecture now zeroes out desired channel when RF is purely real. So in the previous case, if it is purely imaginary, it was zeroed out. Now if it is purely real, it will be zeroed. So if you know whether it is imaginary or real, accordingly you will use the or you will select the circuit. Now I'll look at an overall mixer architecture. Use the in-phase and quadrature demodulation, IQ demodulation or in-phase and quadrature demodulation. So what we do here is use both sine and cosine in the second stage. So in the top and bottom we are using both sine and cosine. You can see there are two mixtures in the top, there are two mixtures in the sine. So irrespective of whether RF is real or imaginary, if it is real, if RF is real, then the real part will be there, imaginary part will be filtered out, will be 0. If it is imaginary, imaginary part will be 0, real part will be there. So that is possible using this circuit. So both real and imaginary parts of RF output, now they will pass through. This is the example of double conversion image reject figure. You don't require this, forget this. We don't require the reference circuit now because your exam is there. Forget this one. I think with this we can take a break today. We'll discuss similarly half an hour or 1 hour for tomorrow. So we'll stop here. Today we'll stop here. ହେଲେ କାଲି ବସିବା